All right, we're back to this one. I had a question on what they're asking. Hey guys, let's get quiet and listen, please. All right, what do you know about cone 1 and cone 2? The circles on the bottom are congruent. What does that mean? They have the same area, right? Same area. What's the volume of a cone?
1/3 times 5 r squared times height.
Good. And in general, hey guys, please be quiet. In general, this is capital B, 1/3 capital BH, right? Aren't these areas the same? And so now we're moving on to the next part of the question. In cone 2, the vertex is directly above a point on the circle. Okay. Well, isn't this directly above the center of the circle? So what do you notice about the heights? Because we all agree, 1/3 doesn't change. Capital B is the same for both cones, yes? So the volumes are going to be the same if the heights are the same. Do you agree? Are the heights of those cones the same? Yes or no? And why? They are. And why? What part, Emma?
Over here says the heights and bases of cone 1 and cone 2 are congruent.
Yeah. And sorry, I'm getting way nerdy on this. There's a term called Cavalari's principle. Not Cavaliers. There's a mathematician, Cavallari, that says I could just read it, couldn't I? That says if the heights of the cylinders are the same and they have the same base area, they're going to have the same volume. Here's what that means. Have you guys ever seen, I'll get your question just 1 second, Tyler. Have you guys ever seen a spindle of CDs or a spindle of DVDs? You know what I'm talking about? Like the old school, like back when we used to record on CDs. There's a spindle.
I don't know what a spindle is.
I'm trying to explain it. A spindle, it has this like rod, and the CDs stack on top of it, and they have a case on it, and you can go to buy them at the store, and they say like CDR, and it's recordable, and like this was after mixtapes. Make a girl a mixtape, ask her out, that kind of deal. So here you make a mixed CD. You download your. Oh, you guys won't reminisce with me?
No.
Ouch. Anyway, you ever seen it? How many of you have seen a stack of CDs like this or DVDs? Okay. Have you ever taken them off the spindle and tilted them?
Yeah.
So are they gonna have the same volume? If I took these off the spindle and put them in a pile and tilted the stack of CDs, yeah, you're not changing anything physically about the CDs, right? Aren't all the CDs stacked up the same volume, whether they're stacked up this way or tilted? That's Cavalari's principle, meaning if the bases are congruent and you have the same height, even if they're tilted, it's called an oblique cylinder, the volumes are going to be the same. This one actually told us. So I've seen questions where they'll actually ask you if these points are both above the cone's base, the same height. Are they going to be the same height? Or if they are the same height, what can you say about the volumes? So just read it too. Yes, Callie.
I'm confused about the question we did before this one, because I got 150.
This one? Pretend that touches. That touches, okay? Now, we've got this. Pretend that's just the front of the box. You can use your imagination, right? All right. If they're asking for the space, they're really asking for the empty space inside, right? Empty volume. Did you read that?
I don't know. I was kind of confused.
So that is not taken up by the globe. So inside the cube, but not in the globe. It's the empty space. It's what's outside the sphere, but inside the box. You with me? So I'm going to take the volume of the box, take away the volume of the sphere, and that's going to be the empty space. Agreed? The volume of the box is what? What's the, let's back up. What are the side lengths of the box? 12 by 12 by 12. So 12 cubed, yes? Cube-shaped box. Which is what page? 28. Minus 4/3 pi r cubed. What was the radius of the sphere? 6. So when you subtract those, tally, plug that in. Be careful, put parentheses around the 4/3. Cube the 6, and you subtract those and get the empty space. Good? All right, next one. This one was kind of challenging. Okay. This one was kind of challenging. They didn't tell you this, but this is actually how, listen carefully, this has really big future implications in calculus and in math in general. It's a really neat problem. I want you to challenge yourself. If you're going to continue in the honors math track, try to be interested and take interest and figure out things like this. It's going to challenge you to be a better student and maybe have some more insight as you learn math. Because by senior year, it's all going to come together. Calculus in some colleges is called analytic geometry and calculus 1. It's wrapping everything up in one. So the interesting thing about this problem is, can you imagine, first of all, drawing triangles in a circle like that? Can you picture what's going on here? Okay, and what happens? What happens if you draw more and more and more triangles? Well, how much space is on the outside of the triangles but on the inside of the circle? Do you agree it would be all this space right here? Can you see it? Right? Now, if I were to keep making more and more and more triangles, what happens to the amount of space outside the triangles but inside the circle? It's doing what? Good, decreasing. Ready? As the number of triangles increases, the amount of space decreases. Do you all agree with that? Okay. This is called this is the foundation of what are called limits. All right, limits are the basis of calculus. So here's what a mathematician once did. Okay, they drew polygons inside of circles like this. Do you agree that's a polygon? If you were to ignore all these little spokes and just look at this, it's a polygon. It's a shape, two-dimensional shape made up of segments. Couldn't you count up the number of segments and call it whatever its name is of a polygon, right? 20 sides, 30 sides, whatever. What if we call this the base of a triangle right here? Can you see where that base gets put into this picture? It's right here. It's right here. It's right here. What happens if you add up all the bases? If there's n triangles?
Perimeter.
You get the perimeter of that polygon. Do you agree? Ready? Next level of questioning. As the number of triangles increases, the perimeter of that polygon approaches the blank of the circle. I'm going to trace all the B's. Are you ready? The perimeter of the polygon approaches the What did it look like I just did? It looked like I traced the polygon perimeter, and it's almost like I traced the what of the circle? Circumference of the circle. Right? As the number of triangles increases, the perimeter of the polygon approaches the circumference of the circle. Do you agree with that? This is the foundation of pi. What's circumference? 2 pi r, yes? Okay. Well, isn't this the diameter? Aren't 2 r's the same as a d? What happens if I divide by d? I get pi. If I, ready? Take yourself hundreds and hundreds of years ago, before they knew how to find the circumference of a circle. They didn't have a formula. They did know how to find the perimeter of a polygon. All right? So what they do? Oh, I want to find how far it is away around that circle. Well, let's make it into a 100-sided polygon. Find one side and multiply by 100. It's really close to what the circumference is. And the more and more and more they did that, they found out if I want to find the circumference, that gets plugged in for the perimeter, right? As it gets really, 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 really close to the circle. So then what? What's this pi thing that keeps popping up? Well, when you take the circumference of a circle and divide by its diameter, you're going to get pi every time. All right. So this is making polygons inside of circles is how we figured out, how they figured out what pi is as a constant. All right, a number. 3.14159 goes on forever. All right, now into the story here. They like to do stuff like this, by the way. Isn't h over 2 the same as 1/2 h? Yes? Times b1 plus b2 plus ... Well, I can distribute this. Watch what I'm going to do up here. 1/2 h times b1 plus 1/2 h times b2 plus 1/2 h times b3. Oh, that sounds like a bunch of area of triangles, doesn't it? 1/2 base times height, 1/2 base times height, 1/2 base times height. All right. So let's get into this and read the claim here. All right. Henry claims that the more triangles the circle is divided into, the closer the estimated area will be to the actual area. Well, if the perimeter is getting close to the circumference, aren't the areas of all those triangles getting closer and closer and closer to the area of the circle? You agree? The area of the triangles added up? All right, so here's Henry's claims. First one. His claim is accurate because as n gets larger, what's n? N is the number of triangles. Very good. The value of h gets closer to the value of r. Let's take a look and see if that's accurate. The value of h gets closer. Oops, nope. This blue is not h. That was the diameter originally. What's h though? Isn't h going from there to there? If you zoomed in, do you agree that's not the radius? Do you agree that's not the radius? But as we make more sides, isn't that gap going to be less and less and less? And isn't that green h going to get closer and closer and closer to r, the radius? Do you see it? So that's good. And the value of all the bases added up. Where are the bases again? Oh yeah, all the bases added up get closer to 2 pi r. What's 2 pi r? Circumference. That looks right to me, doesn't it? Okay, part A. That was a challenging one. Did that make sense, though? Okay. Questions on that one? How many of you got that on your own? Did anyone understand it reading it on their own? No. At least, if you didn't get it right, did you understand what it was asking? No. Okay. There's a lot of symbolic variables in that one. It's probably where we got confused. All right, next one. Did you guys get 15.71?
Yep.
You define the volume of both, and then what? How much larger can the larger cup hold? Nope. How much more water in cubic inches can the larger cup hold than the smaller cup? All right, so find the volumes, subtract. All right, on to the next one. Ooh, the Jupiter problem. All right, calculators are ready to go, right? Fired up, ready to go, warmed up. All right, the volume of Jupiter. 4/3 pi r cubed. Well, the radius of Jupiter I got was 71,492. Here's my plan. I can find the volume of Jupiter. I'm going to take 59.9% of it. That's my volume of Saturn. Then I'm going to plug that in and solve for r in Saturn. And then since they asked me for its diameter, I'm going to double it. Does that plan make sense? Even if you don't understand what to do, does that plan make sense? All right, here's the problem. When you type this in your calculator, what do you get?
Big number.
Big number, thank you. And how is it written? Scientific notation, yes. Okay. So here's the problem. I'm going to type this in. Be careful. 4/3 goes in parentheses. Times pi. Times, and do you know how to type in 71,492 cubed? Caret button to the third power, yes?
Yeah.
All right. And I'm getting a number with scientific notation. What does that mean? 1.53 e to the 10, e to the 15. What does that mean if I were to write it out by hand, Jackson?
That number times 10 to the 15.
Good. So how many decimals would I have to move it over?
15.
15 decimals to get an accurate number to write down, right? Now, here's what we're going to do. Aren't we going to take 59.9% of that? Right? That's what it said. So times 0.599. Right there, even though I don't know what that is, I'm not going to write it out. That's the volume of Saturn. Are you all on the same page with me there? Now, I'm going to keep that in my calculator. So let me write down what I'm going to do. And then a lot of this work has to be in the calculator. So 0.599 times the volume of Jupiter is equal to 4/3 pi r of Saturn cubed. So here's the plan. I know the volume of Jupiter. I know 59.9% of the volume of Jupiter. It's in my calculator. It's in my calculator right now. Okay? How do I solve for r? Well, look up here. Do you agree I have to divide by 4/3, divide by pi, and then get rid of that cubed? Everybody agree with that? So in my calculator, divide by 4/3, enter. Divide by pi, and yes, you could have done that in the same step. I just don't trust my calculator. And then do what to both sides? Well, have you done this before?
No.
What gets rid of a square? Square root. What do you think gets rid of a cube? You guys are so smart. Now, do you know where that is in your calculator?
No.
All right. Anybody have a graphing calculator? All right. Yes. All right.
I made it.
In these calculators, don't type it yet. Okay. Do you see the button It's right above the square root button. It's got an x root of button.
Yeah, I think that's literally what
Now, you can take the cube root, fourth root, fifth root, sixth root, whatever. Here's the thing, though. You have to tell it which root to do. Right now, we want it to be the cube root, the third root, right? Here's how you have to do it in your calculators. First of all, does everyone have, you have to stay with me here. Does everyone have this number entered in as the last entry, as the last line of what we just did? Yes? Okay. So I think, don't type it in yet. Who wants to be my guinea pig? I don't use these often. I think you have to type in 3 and then second in that button and then answer. So I think you have to do 3 and then second and then the X root button and then the answer. I think that's the order you have to type it in. It works? Okay. Here's what's happening. That 3 means you're doing the third root. The second means you're going to access that X root button. Then you hit the button, and then the answer goes under the third root. Now, my calculator, I have to do, I think, math. I have a cube root button of the answer. And I get 60,265.17. So R is 60,265.170. Now, you know it would really stink if you type that in as your answer. Okay? Because didn't it ask us for the diameter? And that's the radius. So you have to double it. So the diameter is 120,530.34. It's a 0. They asked me to go to 3 decimals. I'll put the 0 in there, even though it doesn't affect me. Questions? That's tough. I know the cube root is something new to us. Ready? Let's practice cube roots real quick. These are going to come up in the rest of your math careers. Let's first of all practice with 1 square root. What's the square root of 64? 8. Why? 8 times 8 is 64. What's the cube root of 8? Well, not what times itself gives me a number. What times itself again? 2 times 2 times 2 is 8. So the cube root of 8 is 2. What's the cube root of 27? 3. Back to square roots. You ready? What's the square root of negative 64? What times itself gives you negative 64? No real number. What's the cube root of negative 27? What? Times itself is negative 27. It's negative 3. Do you agree? It's negative 3. So ready? Opening up a whole new world for us. Can you take the square root of a negative number? Can you take the square root of a negative number? Not in this class. Wait till next year. All right? Can you take the cube root of a negative number? Yeah, because a negative times a negative times a negative is negative. Okay? All right, that's what cube roots do. Next. Did you get a rectangle? Next. Did you get a cone? All right, watch up here. Pretend that's our rotisserie. Okay, that's our rotisserie. We're rotating the shape around that. Do you agree B would come up here and go around? This line would get revolved around there, and you get that cone. Take this shape, take the triangle, and rotate it like it's on a rotisserie, and it's going to go like that. When a triangle gets revolved, I don't like the word rotate, by the way. Okay, we're actually doing this in calculus right now, where we're finding the volume of not just a cone, but irregular shapes being revolved around an axis. And I don't know why they use the word rotate. How many of you, when you picture the word rotate, or you read the word rotate, pictured that triangle spinning on the graph, like on a piece of paper, like that?
Yeah.
I kind of, when I read the word rotate, I think the better word is revolve around AC. Just like when the Earth revolves around, like we picture revolving as like that, right? I don't know why they use the word rotate. They didn't ask me. All right, next one. I bet we all got it down to rectangular square. Do you agree?
Yeah.
How many of you went with rectangle? How many of you went with square? Okay, let's break it down this way. Let's pretend this room is the same. Let's pretend this is a cube room. Ready? Let's say this distance from here, I'm on the edge of the cube. Okay, here's a wall right here. What if this is 15 feet? What would the height of the room be? 15 feet. But what about the diagonal from this corner up to that corner? More than 15 feet for sure. Hey guys, it's the same argument as this. S. That's not S. That's the hypotenuse of that triangle. Do you agree? That's going to be longer. All right. Oh, hi, Olivia. All right. Laptops out right now. Laptops out. Where were you, Olivia?
The working on the sidewalk. No, I wasn't. I had to go get my impressions.
All right. Olivia, I'll check your packet.
There's no best.
All right, go to the Canvas homepage, click on the link where it says OST practice problems using the state testing portal. It's just like weird that
It's just you can't breathe through.
Well, I was told that.
All right, everybody, click here. All right, go ahead and do a guest session, sign in. If you're a sophomore, you're getting too familiar with this. You can click on your grade level. Now, we're going to do stay with me here, or else you're going to click on the wrong one. We're doing the geometry spring 21 released items. Geometry, spring 21 released items. Now, some of these you're going to have seen before. All right, we screen captured them, put them in some of the packets you've already done. What we're doing right now is we're walking through the practice testing site just to familiarize yourself with it. So as you click on that, everybody with me? As you click on that, you can just scroll down here. That doesn't really matter. Select, say, skip the test. Like it says like an audio test. You can skip that audio test. And then when it says begin test now, you can do that. Now, again, this is just the practice site. Don't panic. All right. So we're going to work through some of these problems. You're going to do some of it for homework tonight. Now look, as you go in here, when you click on this, here are your options. This one's just going to be a numerical answer. Now, what I want you to pay attention to as well is you can do, like, you can look, here's your formula sheet up here. If you click up there, it'll bring up the reference sheet. You can have a calculator that's used here. I probably use my calculator that I have in front of me, but there's a graphing feature there. I don't know that it's going to really help us for geometry.
How many questions are there?
We'll see. All right. So we're going to do one. Now, you'll notice we already did the Jones problem, didn't we? That was in the probability one. We already did this one. So you're going to do number 1. We're going to skip 2 and 3. So 1, skip 2 and 3. Do number 4. Skip 5. Do 6. We're gonna do 7, and I'm gonna put this on the agenda. All right. Did we do this one? I think we already did that one in the probability packet. Yep. 9. Hold on, Olivia. And 11. All right. So the problems for tonight. One, 4, 6, 7, 9, and 11. 1, 4. Guys, quiet. Guys, let's not grab our phones yet, please. Not until the bell rings. 1, 4, 6, 7, 9, and 11. McKenna, what are you doing? What are you doing? Why'd you grab your phone? I was still talking. Go put it back. Thank you. Everybody understand what you're doing? On the laptops. You're going to write these down in your notebooks as you go, okay?